Okay, let's get started. So we'll continue fraction imputation, but we'll a little bit speed up. So computation, remember, basically we can the information. So when we compute the conditional expectation of the scope function, right? So you have a data, y, whatever, and data and eta. So the dependence, but this is a tricky. The dependence on the parameter when computing the conditional expectation is fully transported to constructing in the fractional weight, right? So if you write this way, you can clearly see that how two different, we have two different rules, right, in computing the conditional expectation. So here this eta is original eta in the scope function, and then this eta is actually reflected in constructing the fractional imputation, and which is used to compute the conditional expectation, right? So then we have two ways of computing estimating the parameter. One is the EM algorithm, which basically right update this way. So this is one way, EM algorithm. You fix, right, given eta hat t, and then you update, and which is M step. So that is the EM algorithm. Another way is just to use the whole thing, right? The whole thing as a function of eta, view the whole thing as a function of beta, and apply Newton method. So which is basically this one. So then Newton algorithm is simply computing the observed scope function and observed information, right? But if you write in terms of the fractional weight, the computation is relatively easy. So it's because you can write it as a fractional weight, right? You can write it as a fractional. So you express everything in terms of the fractional weight. So then this mean scope function is essentially weighted average, right? Weighted average of the scope function, imputed scope function, and then information, observed information is, so when you, so what is the definition of this guy? So the definition of this guy is what? Minus partial derivative of the scope function, right? So S bar eta given eta, something like that. And then because we have two places of eta, right? First one is this guy, and second one is this one. So that's basically what is going on. So, but in the, so if you look at the eta, I mean the fractional weight carefully, actually in fractional weight, you have a dependence on eta in the numerator and denominator. So if you are actually going to do the partial derivative of this fractional, right, computing the partial derivative fractional weight, then you actually have algebra. So maybe this is a good topic for homework. Okay, let's move on. So I will just and then the linearization. So the nice thing about fractional imputation is you can automatically compute the conditional expectation using fractionally imputed data already. So this is pretty much the same linearization, but I will probably just skip everything and move on to section 2, which I think is quite important. You will see a lot of interesting ideas. So, okay. So here's a setup. We have X and Y. and you have a missing and random. So what do you mean by non-parametric? So the difference is that section 1, it is about parametric fractional imputation, PFI. So my 2011 Kim paper, Biometrica. So when I published this paper, I thought this will really save the world, but turns out that is not. But anyway, I think it's still a good idea, but it's a little bit limited because it's a parametric model, right? And now this is a kind of extension, and some of the ideas are actually new. It's just never published. It's just in my head. So anyway, so here's a setup. So now we are not going to we are going to avoid. So the difference is that here we have a parametric model, right? Now we are going to avoid the parametric model assumption. Okay. So but we have a simple setup. So we have a scalar y and missing and random. And so in this case, if you're interested in doing anything interesting, we probably want to do a regression model and regression imputation. Okay. So here's the setup. Basically, we have a respondent and non-respondent. In the respondent, we observe X and Y. In the non-respondent, we observe X and Y is missing. So we want to fill in these numbers, imputation. And let's use notation without loss of observability. Let's just make 1 through R to be the observed data, and R plus 1 to N to be the missing data. Okay. And missing and random. So we don't have to worry about response mechanism. Okay, so then in this case, perhaps the starting point of discussion should be regression imputation, right? So this is a regression imputation. And then you have a beta hat is created from the respondent, I equal to 1 to R. So this is pretty much fairly straightforward, but this is X is to make a p-dimensional vector. Okay, then this is what? This is vector. So p by 1, and this is 1 by p. So then each element is a p by p, right? And then you summation. You take the summation over R. So we are actually implicitly assuming that R is already greater than p, right? Otherwise, you cannot really have cannot inverse, right? So that's a kind of hidden argument for now. And then now the one idea, first observation. So here's a first observation. The first observation is that your yi hat is just the end of the day. It's just a weighted average. You apply, right? So this is your real observation. You apply some weight, fractional weight. So that is actually, you can write it. So each prediction is just the weighted average of the real observations. And so this is your fractional weight. Okay. So this is actually what we call it fractional hot tag imputation. So what do you mean by hot tag? Well, so there's a historical story. So Bureau of Census was established by very early, about 300 years ago. The third president of United States was the first one who made the Bureau of Census. So he's in the money. Do you know the name? Thomas Jefferson. So you have what is Republican and so the two-party system. Where we can actually Google it quickly. First director of Census Bureau. Oh, no, not this one. Okay. Well, I will I'll figure out and not well, commerce maybe. Well, this is not really big deal. Let me quickly. So anyway, so the main thing is that Bureau of Census existed before the invention of a computer, right? So then, how the employee of Bureau of Census do all the census job at that time? Think about that. They have a card, so they have a card. So there's some big storage room, and then one room is for Iowa, right? One room is for Kansas, essentially. And then you have a lot of drawers, okay? And then each drawer you have a deck of the card. And in the card, each one page of the card, one card represent one household. Okay, something like that. And then the deck, whole deck will probably for one county, right? For example, Story County has a one deck. And so something like that. So then what do you mean by hot deck? So when they go out for interview, right? The enumeration, some houses do not cooperate, right? Missing. I mean, nobody really open the door and answer. Then but they know that there's somebody in the house, but they just don't want to cooperate. Then we have to do imputation, right? So then one way of doing the imputation is just use the same deck to replace at random. That is a hot deck. Okay. And cold deck. So there's actually another version. Cold deck is that go back to the old census. Okay, 10 years before, because the census occurs every 10 years. So go back to the 10 years before record and pick up the corresponding household and then replace. That is called the cold deck. So hot deck means that we are using the current data. Okay. So anyway, so that is basically why this Y is. It's not really old data. We are using the same data. So that is the limit. Anyway, so fractional means that we are using some sort of we are splitting, right? We are doing a fraction, not 0 and 1. It's between 0 and 1. So, but interesting part. So this is the fractional weight, and Wij. Basically, we are interested in imputing. So we are interested in imputing I's unit. So that means we use Xi, right? But for Yj, so we have others, right? They are actually not the same person. So the different one. But for Yj, we have Xj, right? We use Xj, and then this is our weight. So note that this is 1 by P, this is P by P, and then this is P by 1. So you are end of the day, you just apply some scale of weights to each element.
So this is used least square.
Huh?
This is used like the ordinary least square.
Yes, exactly. It's just the least square.
So what if we use some more like machinery and non-parametric estimates? Then
I feel like to cover it later.
Okay. I just think the tool will not be always able to write in this.
Yeah, so this is, I start with a simple setup, and then we'll move on to more difficult one later. So yeah. So stay tuned. Okay. So one property is that if you apply, so this is actually originally, this is where yj, right? So instead of yj, if we use xj, then it goes back to xi. So then what is the implication? Well, let me first show this. Okay. So why this is true? Well, that is actually quite easy to prove it, but let's just do it for one time. So this is xi prime summation. So this is k xk prime inverse summation j equal to 1 to r xj. So we can use xj prime, right? So that is because this guy the whole guy is actually equal to this. So, right? So this is basically what I did. And then you can see that this is just the same thing, right? So we have a cancellation. So that means you end of the day, you get xj prime. So which means, oops, what am I? Okay, no, sorry. What xi prime, right? So this one remains, and then this just cancelled. Okay. So one implication, what is the implication of this property? Well, suppose we have exactly explained. So xy is completely explained by x linearly. That means what? Your yi hat is what? Your yi hat is j over 1 to r wij star yj, right? So that is this one. So this is definition of and then this is wij star xj prime beta. And so that means your xi, well, no summation. That is xi prime beta. So that is 4. That is yi. So basically, yi hat, the imputation for yi is exactly equal to yi. So no error. So you have a perfect, right? Perfect, I mean, very accurate imputation. So that is actually, comforting. I mean, that is good news. Okay. Now, first remark is this. So you have in general, you have an error, right? In general, you have error. So then if you use this linear class as a predictor, then what is the mean scale prediction error? So that's under this model, you can write it. So basically this one, so you plug in here, right? And why this I is different from one of it, right? Because it's missing. So this is actually missing, but still you can compute it under the model, right? So then you can actually compute so square expectation is the expectation, expectation of square is the expectation square of the expectation. There is the mean part and then variance. Okay, so that is the mean scale prediction error under the model. It turns out that the regression fractional weights, the solution here. So the form is actually the solution to that minimize this one, subject to its mean part is equal to 0. And how to show this? So how to show this? Where this is a, so we are, so these x's are given, and we are interested in finding w. Okay, so this is a quadratic optimization problem. I mean, constraint convex optimization problem. So it's easy to solve. So method 1 is just to use the Lagrange multiplier method, right? So minimize so Q W lambda is minimize J W I J star square plus lambda prime J W I J star xj minus xi. So if you solve this, you'll get a solution. Well, that is a standard approach, and you can easily check. But there's actually, this is more like a mathematical approach. And actually, I have another idea to solve this kind of problem using a statistical tool. So how we can interpret? So my point is that how we can interpret this optimization problem. Let's minimize this one subject to this one as a statistical problem. One way is to minimize this. So here this is a constraint. Here this one doesn't seem to be a constraint, but it is actually constraint if you let sigma 0 goes to 0. So if you set sigma goes to 0, that means what? You are interested in minimizing this one. But this is, so this one, setting this one 0 means that you are mainly focusing on this one. Right? So you really want to this constraint to be satisfied in the beginning, and then minimize this one overall. Okay. Well, you may wonder why we bother this, but let's see. And then because you can, this is exactly regression problem. If you do view this way, this is y. Okay, this is beta. Okay, this is X matrix. So you can frame it as a OLS, a GLS problem. And then this is V inverse. Okay, so that this is very, popular tool in linear model, right? So you can directly apply the solution. You know the solution already, this kind of problem, right? So the solution to this one is what? Beta head is x prime V inverse x inverse x prime V inverse y. You know that already. So then that means we just apply. Okay, so this is y. So then this one becomes this. And then this one becomes this. Okay. And so that is solution. But this one turns out to be so this is actually R by R inverse. And but there's a very simple linear algebra that uses P by P inverse. So, and why this is equal? You just we use this one. You basically move this to here, move this to here, then you can check they are actually equal. So, and then end of the day, you will let sigma square goes to 0. Okay, so you will let a sigma square goes to 0. Then this is what? This is the what we want to show. I'm sorry.
That's the place the root has take a form similar to range regression.
Yeah, well, this one actually, that's a good question. We'll move on to Ricci regression. So Ricci regression will have, in the Ricci regression, you have this one will be general, I mean lambda something, right? But here we want this to be constraint. So you're right. You can this could be viewed as a special case of this Ricci regression in some sense. Well, okay. So it's just one way, but it's not really a big deal. Let me move on. So let's try to understand what is going on here, really. I mean, what is the meaning of what is this matrix is doing, really? So let's use a very simple case. Yeah.
If you go to the page that's right here. So I think this actually related. So if you go to the previous page, so our goal here is to take the bias into 0,
Right.
And then minimize the variance.
Right.
But for a high-dimensional case, so if X is high-dimensional, so this is not doable.
Right.
So we need to allow some bias.
Right.
And then minimize the variance.
Exactly.
So then what people do is to put L1 constraint on that bias part.
Okay.
So the maximum of that bias is less than lambda.
Right.
Okay.
Right.
So, but I think your idea is to replace the L1 constraint by L2 constraint. So if you go to the next page.
Right. That is actually L2 constraint, right?
Right. So if so that actually change the objective function equal to lambda times the sum square of the bias.
Right.
Use your QWI.
Here.
Yeah, it's the sum square of the bias.
Right.
Right. Yeah.
Right. Yes. Yeah. Okay. Yeah. Agree. Yeah. So this is kind of a starting point of the discussion that I plan to move on. So now let's see. So let me first what is going on here, right? How you really do simplification. So one interesting part, so this is actually, if you are familiar with the linear algebra projection matrix, right? This is x prime, x inverse, x prime, right? So this is actually the element of this. I mean, this is element of the projection matrix essentially. So, and then one interesting property of the projection matrix is that it's invariant with the column space as long as the column space is same. So Px equal to Pg, right? So as long as you have the same column space, you get the same matrix. So that means whether you use this one or whether you use So you can, you see what I'm trying to do? So basically you have a two different vector, but gives the same space, same column space, but this is better because it gives, it's orthogonal, right? This is already orthogonal, the columns are orthogonal. So then the inverse is very easy to, so my point is that this one, you can write it as a C, I, J, right? So that if you write this way, this is diagonal matrix. So this one turns out to be what? This one turns out to be R0, 0, summation xi minus x bar r square. Okay. So that way you can actually, so that is why you have this 1 over r. And then this one is mean adjust. Okay. So that is kind of a typical trick that we use for this kind of algebra. I mean, having a good big picture is important, but also we need to really have all kind of skills, computational, techniques we should be familiar with in order to do anything, right? So anyway, okay. So now let's really take a look at what is the behavior of this weight. So now let's use a very simple toy example. So I have a r equal 5. X1 equal xj equal to 1 equal 1, 2. The actual value is 1, 2, 3, 4, 5. Okay. And my constraint. So the constraint I have is what? J equal to 1 to R Wij star equal to 1. That's one constraint. Another constraint is Wij star xj equal to xi. So that is my constraint. And this, I have this xj equal to, so this is summation is 1, 2, 3, 4, 5. See? And then this is my control. Okay. So if I use this one, the originally they are already means equal to 3, right? So then really the second one doesn't really necessary. So then you have equal. And then 4.5 turns out that this is what you get. So basically the sum of these, right? Sum of this equal to 1. And some weighted sum of this one, right? So this one times this plus this one times this, right? Equal to 4.5. Okay, so you can see that linear weight. So this is kind of a regression, right? Regression fraction weight is really, this is same interval. The interval is same. So what is, you have a 0.015, 0.015, right? You just add them, keep adding. Because this is essentially your slope. Actually, the other one. Sorry. This one. This is your slope. This is your slope. And this is, right? You have 1, 2, 3, 4, 5. Okay.
But this is just one set of the solution. It's not unique.
This is one unique solution to this optimization problem. So if we use this one as a optimization problem, we have a unique solution, right? But if you change it, right? I think that is what you want to say. If you change this objective function, then we have a different solution. So because we have how many? So we have here for fixed I, we have how many? So R unknowns, P constraint. So the number of equation here is a p-dimensional. But W, we have RWs, out of them, right? So and we already started assuming that R is greater than P. So that means we have an infinitely many solution. Okay, infinitely many solutions. So then this one itself doesn't have a unique solution, but to make a unique, you need to use an optimization function to uniquely determine, and you can use least square because we are talking about here. We are using this. So if you use under this linear model, this is the mean square error. So this makes sense, right? We use this one as a optimization function. So minimize the variance subject to bias equal to 0. Right? That is the basically what this is about. Now, so this is very well defined problem, but the weakness is that you can see that the weights can take negative values. So that is the one limitation. So to resolve these issues, there's several approaches, but we'll move on for now. Okay, so here's how we're gonna understand this fractional weight. So you can see that this weight, if you look at this weight carefully, so I is given, right? I is fixed I, you just change J, right? You change J and look at over J and see which one has the maximum. That is when xj is equal to xi, right? Then they are squares. So then it should be the highest. So that is the one observation. So that actually gives, so that is this one. So for each one, we are trying to impute. See, so the implication is this. We try to impute, right? Impute these numbers from this one. And then I use this hand matrix or fractional weight to assign the probability, essentially, right? Essentially the probability, but unfortunately, it's not really probability because some of them are negative. But still, it gives some idea of which one is close. And then one message is that the fractional weight will be highest for particular here, the weight. So I have a R assigned, and then which one is the biggest depends on how close they are in terms of X. So that's really close to nearest neighbor imputation, nearest neighbor matching based on X, right? You compare X and pick one with the smallest distance in terms of X. So that actually gives some very interesting interpretation, which basically means that you can view it as a corner function. So corner function is you have a two input, okay, two input, and gives a scalar. And then, but this weight is actually this particular corner function should satisfy property 4. So property 4 is what? This one, right? So we should give back to our current xi, which is very close to the concept of the reproducing corner. So I don't know how many of you are really familiar with this reproducing corner, but this is reproducing property is essentially very close to idempotent matrix. Okay, it gives back to if you multiply, operate, end of the day, it gives back to what you start with. So the problem with the linear regression is that this corner function it can be negative. So we can actually view this one as a corner problem and impose, corner function should be non-negative. So then this is a way to move on. So naturally, maybe one way is to relax exact balancing. So by the way, this replacing property, if it satisfies the replacing property for each xi, then it's actually is equivalent to leads to the calibration property or covariant balancing property. But we'll see what it means soon. Okay, so here Ricci regression. So naturally we probably want to use a penalty. So like this. So then still, this is a regression problem. One regression problem. Then we know how to obtain beta hat, right? Which is kind of this mixed model equation. And then turns out that it is still fractional imputation. Fractional imputation, right? Okay. So basically, see, this one is what? Xi prime beta hat still, right? And this beta hat is this one, the solution to this one. So that means you get, so X prime, right? X prime, and then matrix, right? And then inverse, and then X prime J, Xj, sorry, no prime. So this is basically the X prime X matrix times the Ricci part, right? Shrinkage factor. And we intentionally separate X1 and X2, separate out, because here the idea is if you do this way, you can show that you get exactly the reproducing property for X1, but not X2. Which is good because X1, for example, X1 should include the intercept. Okay. Otherwise, this way doesn't add up to equal to 1, which is not good, right? You really want your fractional weight to add up to equal to 1. And how to, okay. So then how to prove this? Well, so you can write it. Okay, you can write it. So let me. So what is this? Wij star is xi prime r prime xr plus omega. I mean, well, let's write it this way. Here, x1 prime x1, x1 prime x2, x2 prime x1, and x2 prime x2 plus I lambda iq inverse x j. See, so this one xi is x1 I, x2 I, right? So that is p dimensional, q dimensional. And then what is x1 prime x? X1 prime x is you have a x1 1. So you, okay. Let me write it this way. So what is x1? So you have out of them, right? So x1 1 2 x1 r prime prime. So that is r times p matrix. Same way, prime 1 2 x2 prime r. So that is r times q matrix. So it's just making I just make the design matrix for 511. Okay, and then so that x1 prime x is just x1 is p by p, x1 prime x2 is p by q, right? We have so that is basically what is going on. So then really what you are trying to show is what we try to show is to compute is over j over the wij star xi 1 I. So that is what we are going to check, right? This is 1j, sorry. Really confusing. So xj 1j. Okay. So that we want to compute using this matrix. We want to do this matrix algebra. And so how to do that? Well, okay. So let's basically let's do this way. I prime. So you use this one. Then we can do the same thing. So xi prime, x1 prime. So note that the summation only applies to the j. So then we can move on the summation all the way. And summation is here. J equal to 1 to r. And then what is xj? Xj is x1j, x2j. And then you have a xj 1j prime. So this is too small. But I can always. Okay, so this one, right, is this here, and this the whole thing is a weight times summation. And then my point is that, and then you can write it as a x1 prime, x1, x1 prime, x2, x2 prime, x1, x2 prime, x2 plus lambda iq inverse times, this is actually nothing but x1 prime, x1, x2 prime, x2, x1.
Should that be the x1j comma x2?
You mean
No, before, yeah.
sorry. Can you say again?
Should that be a row vector? Yeah, a row vector. A row vector of x1j and x2j.
This one.
Yeah.
So this is a column vector, and this is row vector, so that you can have this one.
Yeah, but we have in WRJ style we have xj, where xj is xj has two pieces.
Yeah, this is a little bit confusing, but this is, so for example, this one is a summation I equal to 1 to r x1i x1i prime.
Yeah, yeah.
Right? So that is basically what is going on here. So we have a 1j prime, which is 1, 1.
Mhm.
Okay?
Oh, okay.
Okay, okay. So then, okay, here's a magic. So the magic is that you can express, so okay, I don't have much space, but I will try. You can express this one as the whole thing times I, this is P by P, right? P by P, P by P, 0, Q by P. So, so if you, so this matrix is nothing but this, taking the first column, which is this one. So which is multiplying this one. Okay. Then why we are doing all this headache? Well, now you can cancel, right? You can cancel this one with this one. And then you can greatly simplify, because this is the whole matrix cancelled. And then only thing is left is this one, which is applied to here. So that you get actually obtain x1i. That is what you want to show. So you can, well, okay. So that is, well, this is just a matrix algebra, but the implementation is a little bit kind of interesting, because you do this kind of rich shrinkage to the second component only, but not the first component. That way, so here's a point. If you increase lambda to a lot, So if you set lambda equal to 0, for example, so let's consider two extremes. One is lambda goes to 0, the other extreme is lambda goes to infinity. Okay, so lambda goes to 0 means what? Lambda goes to 0 means just the regression calibration, right? Regression, regression using x1 and x2. That will basically make the exact reproducing for x1 and x2, right? But it will create a lot of, so you have a lot of inverse matrix, higher dimensional matrix, so that you will get a good chance of getting negative weights, right? It's variation, a lot of variation in the weight. Another extreme is you set lambda equal to infinity, move infinity. That means you will create a lot to the denominator part of the matrix. I mean, if you think about this, so you are taking the inverse, right? And then this one is a kind of a square product. So you put high values in the denominator so that the variation will be smaller. So the weight will be less variable, but still achieves this one. So sometimes some literature, this is hard calibration. This is a soft calibration. Soft. So we have in practice, we have a very important variable to control and less important variables to use. So then the important variables you may want to achieve exact balancing, right? But some so important variables, you can just put it to the model, but kind of relax a little bit. So that is the kind of idea here. Okay. So yeah, so a lot of algebra, but the practical implication is, I think, quite interesting. So that is what is going on. So you can do the same thing, right? You have a mixed model, right? You have a mixed model now, and then compute the mean square prediction error, and then you get the same form. So here previously we just have this term and this term, right? But now we have this term. Okay. And so that this term, previously this term was a constraint, but now this term moves to the objective function. So we wanna still do balancing, but not as a constraint. Okay, if this guy is moved to here, then it is exact balance, right? Exact balance. But that is probably too much. So we want to do it, put the max optimization objective function, and so that we can kind of relax it a bit. So that is basically the idea. And then so you can formulate it as a same GLS problem, and then solve this. So that is basically the idea. And now, that's not end of the story. We can move on. So we have a lot of interesting, penalized regression, right? So we can do the same thing, in some sense. So, okay. So more generally, maybe we can use penalized regression to develop the imputation, right? So naturally. And then same thing. And then first thing to make sure is that we want a bias correction. In the sense that we really want the residual equal to 0, some of the residual equal to 0. Otherwise, we are not really have this form, right? So that is so we put this one. So basically we have one way to achieve that is we have a beta 0 separately here, and then penalization should not apply to the intercept. Okay, so you can, one way is to, I think this is probably better notation. If you do this one plus P1 beta 1. So if you do that, then we always satisfy this, right? Because we don't do any penalization on beta 0, but still do penalization on beta 1, which is the slope graph. And then you can use that, then you can still write this here, right? For some omega, I mean, diagonal. So this will be, so this is actually essentially a diagonal matrix of the partial derivative beta 0 p lambda beta 1 beta p lambda, right? So this matrix should be diagonal matrix. Okay. And then now, what's next? Well, here's a, so we know this is x bar n prime beta hat, right? This is the regression imputation. So this is the regression imputation. So we can first add beta star and subtract. Okay, that's no problem. First line is no problem. Second one, we know the form. We have a closed form of the beta hat, right? Lambda. So we have a closed form, so we can write it, which is this one. Okay. Well, I think this is not really correct. There's actually some additional term corresponding to, yeah. Okay, so let's do what, yeah. So remember, this one is what? So this idea has not been really peer reviewed. So probably that's why it may have a mistake. Okay, so this is the beta hat, right? Beta hat lambda. And now we want to do some subtraction. Then we basically compute the same thing here. And then what we are doing is minus I prime beta star. So beta star plus some additional, I mean minus, right? Minus omega. So one way, no. So we have omega plus.
I'm thinking, to find y, probably we need to write in terms of 2 beta. The y is equal to x I prime times 2 beta plus error.
Okay. You mean like this?
Right.
Okay.
Plug that in.
Well, I think so my point is, what I missed is there's actually additional term which is which has to do with omega, because if you apply to this matrix, so you multiply this matrix to here, you get this one residual plus something has to do with omega. Okay, and then I think we need some conditions to make this omega to be negligible, and then after that everything is remains the same.
There is some true parameter that in Y is the beta from each one, but here the beta star is not equal to that beta.
It doesn't matter because I mean this can be anything. Okay, this we can. I mean we are okay. My point is okay. So let's just write it as something like whatever. So if you have this kind of form, then what is this? So if this is anything. Okay, so we are trying to doing the same thing here, but we have additional comes in, and so there may be some trick necessary to control the order of this omega from here. But the point is, once you do that, then this is actually algebraically written as a sum of the fractional weights. And so then the sum of the fractional weight over I is actually a kind of propensity weight. So you end of the day you get this kind of nice form, and then you can use that as a linearization. But I made a mistake. There's some condition that requires to control the order of the remainder term. But it should work for rich regression at least, because rich is just nothing but additional observation. So you can write it, still view it this way, just additional observation. Okay. And so that is the main point. And then in the lecture note I have a nonparametric regression, nonparametric kernel regression, and that has a lot of details. But one thing I like to point out. So if you use nonparametric regression to do imputation, you can still write it as a fractional waveform, fractional imputation form, and then turns out that in the linearization, the weight omega can be actually adding up the fractional weight. So point is, this is a linear in Y, linear in observed Y. So you can actually calculate what exactly is the contribution for the observed Yi, particular Yi. That Yi is the weight, and this weight can be used to construct the variance estimation. But for linearization, but the theory behind all this requires some additional techniques, but I'm not going to talk about that. But another interesting part is that this paper is that usually nonparametric regression, the convergence rate is slow. It's not routine and consistent because it's a nonparametric. But turns out that in the context of imputation, you still get between consistent model like a parametric model. That is regarded as a kind of surprising result at the time, but it's not really surprising anymore. People surprised at the time, and so you cannot really keep surprising, right? So well, I will probably skip because this is a little bit beyond that. If you are interested, you can probably check check the paper or my book. In the book, I have actually the proof proof for this theorem, and I may upload the sketched proof in the as a note. I have a note for proof, but it's probably too much for this class. So any questions for this?
How is this related to the couple one estimation? Using combining the.
That's right. So really yeah, that's a good question. So I already, this is kind of a hint already, right? I mean, this omega seems to be the inverse of the probability, right? Expansion probability.
Right.
And so then this, and also this form itself is a doubly robust form in the sense that if this is the inverse of the probability of response, then you have a cancellation, and then this will be unbiased, right? So
Yeah, but how to use that in the omega, in the open score model?
well, actually, so that is the part of the materials that I plan to cover in chapter 7. But the proof, so that is the proved by Fuller, 1994, and also so basically his argument is that this so Wi contains, so okay, actually inverse, so pi I is in the column space of X. So if this one true pi I inverse is in the space of the column space X, then this regression estimator. So regression estimator here has a double robustness in the sense that it is unbiased for the regression model, or it is unbiased under the model assumption about the probability, propensity, where this probability, inverse of the probability, is in this column of the X.
So under this assumption, we basically do not need to model the potential.
This is already a model for propensity score.
Okay. But we just do not need to estimate the potential score. We just directly do the regression.
Some sense, right?
Estimate
So
the
under this assumption, right? So yeah, right. So that is the point, right? You usually one way is you use the assumption, right? Something like this, and then estimate it. That is the one way. Another way is just to assume that this one is in the column space of X, then you don't have to. So two approaches. And the second one justifies the use of the Y regression estimator is justified under the response. But that's for chapter 7. You are now in chapter 6. So you are once next week. Actually, we'll cover the next week.
But if we use the first approach, I mean also like write in terms of some optimization for we, but also combine the model for the potential.
Yeah, next week.
Okay.
Okay.
Page 20.
Very good.
Yeah, because for non-parametric regression, we have some kernel that's
Right.
simply ij, then change wij star as a special case of because it also satisfies
So
that
this is,
just li equals to wij.
so, right, this is actually fractional, the form of the fractional weight. Right, so I think that is what your question, so you can write it as a m hat xi, which is the j equal to 1 to r summation of l. This is not really good notation, but xi j. So you have lj xi yi. Okay, and then point is that you can, this is actually wij star. So is that your question?
Yeah, I think because for this li, we can choose different kernel function k.
Right. So then you have a different choice of function.
Is the wij we defined in the previous slide just a special case of such li?
So this way you get so this is the fractional weight, but using using a particular choice of the kernel function. And this is a non-parametric regression. Okay, and then yeah, this is basically how much you want to weight, right? How much you want to weight, and linear model we use the weight in a linear form. So in the linear basically in the linear regression we used something like beta j no, basically beta I0 hat plus beta hat I1 xj. So in the linear regression we use this kind of weight essentially. This one is nonlinear as a function of x. Okay. But this way you can avoid the negative weights automatically because you start with the non-negative kernels. Okay, I think that's all. Have a good weekend and see you next week.